One day, humanity will face a hard truth. The stars are not waiting for us. They are not welcoming. They may not even be reachable. For over a century, scientists have studied the laws of the universe with one silent question in the background. Can we ever leave our solar system? Not send a signal, not send a probe that drifts for thousands of years, but send people, real, living humans. And the answer that keeps appearing is uncomfortable. The universe may have built a wall we cannot cross. Traveling to another star sounds like a problem of technology. Build a bigger engine, design a faster ship, gather more fuel. That is how progress has always worked on Earth. Horses became cars, cars became planes, planes became rockets. So naturally, the next step feels simple. Go to the stars. But space does not play by Earth's rules. The physics that governs the cosmos is strict. It does not bend for ambition, and it does not care about human dreams. The nearest star system, Alpha Centauri, sits more than 4 light years away. That number sounds small until you understand what it means. A light year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. Even at that unbelievable speed, it takes more than 4 years to arrive. Our fastest spacecraft would need tens of thousands of years to make the same journey, not decades, not centuries, tens of thousands of years. That is longer than recorded human history. And distance is only the beginning. In the early 20th century, Albert Einstein revealed something that changed everything. The speed of light is not just fast. It is the ultimate speed limit of the universe. Nothing with mass can reach it. As an object moves faster, it becomes heavier. To push it closer to light speed requires more and more energy. To actually reach that speed would require infinite energy, not a lot of energy. Infinite, that single rule may permanently block interstellar travel. Even if humanity somehow gathers enough power to approach light speed, another problem appears. Time itself begins to behave differently. Clocks on a fast-moving ship tick slower compared to clocks on Earth. A crew traveling near light speed could experience only a few years. Meanwhile, decades or centuries could pass back home. Interstellar travel becomes a one-way leap into the future. The travelers would return to a planet that no longer remembers them. And space itself is not empty. Between stars lies radiation powerful enough to damage cells and electronics. Tiny particles drift through the darkness at extreme speeds. Even a grain-sized speck becomes a deadly projectile. Shielding against that environment would require massive protection. More mass means more energy. More energy means more fuel. The problem grows in a vicious cycle. Some physicists have explored radical ideas. Concepts like warp drives and wormholes appear in equations. The math behind the Alcubierre drive suggests space itself could be bent. But there is a catch. It would require exotic matter with negative energy density. No confirmed supply exists. No experiment has proven it can be created in useful amounts. The equations allow it. Nature may not. In this video, you will learn why distance is only the first barrier. You will understand the true meaning of the universe's speed limit. You will see how energy demands explode beyond imagination. You will discover why time dilation turns heroic missions into irreversible sacrifices. And you will explore the lesser-known dangers of radiation and interstellar debris that most discussions barely mention. By the end, you will see that interstellar travel is not just an engineering challenge. It may be a direct conflict with the deepest laws of physics. Stay with me until the end, because the final piece changes the entire perspective. It is not simply about whether we can build a powerful enough engine. It is about whether the universe was structured to keep civilizations isolated. The answer is not emotional. It is mathematical. Welcome to our channel, where we explore the truths that reshape how you see reality. If you want clear explanations, deep ideas, and the kind of science that challenges assumptions, subscribe now and join us as we uncover what the universe really allows. Space is not just big, it breaks the way the human brain measures size. On Earth, Distance means hours in a car or days on a ship in space. Distance means numbers so large they lose emotional meaning. The closest star system to us, Alpha Centauri, is about 4.37 light-years away. That number sounds almost friendly, just 4, but a light-year is not about time. It is about distance. It is how far light travels in 1 year. Light moves at about 300,000 kilometers every second. In 1 second, it could circle Earth more than 7 times. In 1 year, it travels nearly 9.5 trillion kilometers. Multiply that by 4.37. That is the gap between us and the nearest star. Now compare that to the fastest human-made object ever built, NASA's Parker Solar Probe. It can reach speeds around 700,000 kilometers per hour at its peak. That sounds extreme. At that speed, you could fly around Earth in minutes, but against interstellar distance, it becomes almost nothing. At similar speeds, reaching Alpha Centauri would take thousands of years. Not a long mission, not a multi-generation project. Thousands of years. Civilizations rise and collapse in that span of time. Voyager 1, the farthest spacecraft ever sent, has been traveling since 1977. It has not even traveled 1 light day from Earth. Not 1 light year. 1 light day. And it is already considered one of humanity's greatest engineering achievements. That is the scale we are dealing with. Interstellar space is not just empty darkness. It is a desert so wide that even our fastest machines barely move across it. Distance alone already feels crushing, but then physics adds another rule. In the early 1900s, Albert Einstein introduced the theory of relativity. One of its core ideas is simple but brutal. The speed of light is the maximum speed anything in the universe can reach, not a suggestion, not a technological limit, a fundamental property of reality itself. Nothing with mass can travel at that speed. As an object moves faster, something strange happens. Its mass increases, not in a visible way, but in terms of the energy required to keep accelerating it. The faster it goes, the harder it becomes to push it even faster, close to the speed of light. This effect becomes extreme. To reach light speed would require infinite energy, infinite. That word is not dramatic language, it is literal. You would need more energy than exists. So even if humanity builds a perfect engine, even if materials become stronger than anything we know today, there is still a ceiling. You can approach the speed of light, you can get very close, but you can never cross it. The universe enforces that limit everywhere. Every experiment ever performed has confirmed it. This changes the problem completely, because even traveling at half the speed of light would be a massive achievement. Yet at half light speed, reaching Alpha Centauri would still take almost 9 years. That is one way. And accelerating a spacecraft to even that fraction of light speed introduces another monster. Energy. To accelerate a relatively small spacecraft to a significant fraction of light speed would require energy comparable to the total yearly energy consumption of entire nations. Push closer to light speed, and the required energy approaches the total annual energy production of the entire planet. And that is just for acceleration. You also need energy to slow down when you arrive. Otherwise, you simply fly past your destination at unimaginable speed. Think about that scale. Humanity's entire global energy production for a year focused on launching one ship, not powering cities, not running hospitals, not growing food, just accelerating a single vessel. And as speed increases, the energy demand does not rise gently, it explodes. And energy is not just fuel, it becomes heat. It becomes radiation, it becomes engineering stress. Storing that much energy safely would require technologies far beyond what currently exists. Chemical rockets are nowhere close. Nuclear fission helps, but not enough. Even nuclear fusion, which we have not yet mastered for stable power generation, would struggle to provide what is needed for near light speed travel. The deeper you look, the clearer the pattern becomes. Distance stretches beyond intuition. Speed is capped by the structure of space-time, and energy requirements rise toward impossible levels long before you ever reach another star. But let's say we somehow solve energy, even if we somehow gather the energy, even if we build an engine powerful enough to approach the speed of light, another consequence appears. It is not mechanical. It is not about fuel. It is about time itself. According to relativity, the faster you move, the slower your time passes compared to someone who stays still. This is called time dilation. It is not science fiction. It has been measured with atomic clocks. Astronauts on fast-moving spacecraft age slightly less than people on Earth. The difference is tiny at normal speeds, but near the speed of light, the effect becomes extreme. If a crew travels at 90% of light speed, time for them slows dramatically. A journey that feels like 5 years on the ship could mean decades have passed on Earth. Push the speed even closer to light, and the gap grows wider. 1 year for the travelers could mean many years for everyone else. From inside the spacecraft, the mission feels possible. The crew eats, sleeps, talks, plans their arrival. They experience a normal flow of days, but Earth is racing ahead in time. Families grow old, friends disappear, nations change, languages shift. By the time the travelers return, if they return, centuries could have passed. Interstellar travel becomes a one-way leap into the future, not because the ship cannot come back, but because time does not move equally for everyone. The people who left would no longer belong to the world they returned to. Everyone they loved would be gone. Every familiar place would be different. History would have swallowed their entire generation. And this is not a technical glitch that can be repaired. It is built into space-time. The closer you move to light speed, the more severe the separation becomes. You can reach the stars, but you may lose your entire era in the process. And we're still not done. There is another assumption people often make, that space between stars is empty, a perfect vacuum, a silent void. In reality, interstellar space is thin, but it is not nothing. It contains radiation, high-energy particles, stray atoms, dust grains, magnetic fields, the leftovers of ancient supernova explosions. Cosmic rays move through the galaxy at nearly the speed of light. These particles carry enormous energy. When they strike living tissue, they can damage DNA. On Earth, our magnetic field and atmosphere shield us from most of this radiation. Outside the solar system, that protection fades. A spacecraft traveling for years through interstellar space would face constant exposure. Shielding against this radiation is not simple. Thick layers of material can help, but more shielding means more mass. More mass means more energy required for acceleration. The same problem returns again. Every solution makes the ship heavier. Every kilogram multiplies the energy demand. Then there are micrometeoroids, tiny grains of dust. In everyday life, a speck of dust is harmless, but at a significant fraction of light speed, even a grain the size of sand becomes a projectile with enormous kinetic energy. The faster you move, the more destructive even the smallest collision becomes. At near light speed, space turns dangerous. Invisible particles become bullets. The front of the spacecraft would need extreme protection, not just against one impact, but against countless impacts over years of travel. One serious strike at those speeds could release energy comparable to an explosive blast. Designing shielding that can survive that environment without becoming impossibly heavy is another unsolved challenge. And again, the faster you go, the worse the problem becomes. And then comes the biggest wall. Some physicists have proposed ways around the speed limit. One idea is the warp drive, often linked to the Alcubierre concept. Instead of moving a ship through space faster than light, the idea suggests bending space itself. Compress space in front of the ship, expand it behind. The ship would sit inside a bubble of space-time. Locally, it would not break the speed limit, but the bubble itself could move faster than light relative to distant observers. On paper, the equations of general relativity allow this possibility. The math does not forbid it, but there is a catch. The warp bubble requires exotic matter, matter with negative energy density, something that has never been observed in usable quantities. Small quantum effects hint that negative energy might exist in tiny amounts, but nothing close to what would be required to move a spacecraft. Then there are wormholes, hypothetical tunnels connecting distant points in space-time. Step in at one location, step out near another star. Again, general relativity allows solutions that resemble wormholes, but keeping one open would also require exotic matter. Without it, the tunnel would collapse instantly. The mathematics offers possibilities. Physics demands proof. And so far, no experiment has shown that these forms of matter can exist in stable, controllable amounts. The equations are flexible. Nature may not be. When you place all of this together, a pattern emerges. Distance stretches beyond human intuition. The speed of light sets a hard ceiling. Energy requirements rise toward extreme levels. Time separates travelers from their own civilization. Radiation and debris threaten destruction at high velocities. Theoretical shortcuts depend on substances we have never confirmed. It is not just that interstellar travel is difficult. It may be woven into the structure of the universe that moving between stars is restricted. The scale of the cosmos is protected by laws that do not bend easily. Each barrier connects to the next. Distance links to speed. Speed links to energy. Energy links to mass. Mass links back to speed. Radiation and time sit quietly in the background, waiting. And the deeper we examine the rules of space-time, the more it feels like the universe was not designed for easy crossing. The deeper we go into the physics, the clearer the picture becomes. The universe is not just large. It is structured. It runs on laws that do not bend for ambition. Distance stretches beyond comprehension. The speed of light stands like a permanent ceiling. Energy demands explode long before we get close to another star. Time itself separates travelers from everything they once knew. Radiation and invisible debris turn empty space into a battlefield. Piece by piece, the dream collides with reality. The universe has rules, precise, unforgiving, elegant. And those rules may lock the stars away from us, not because we lack courage, not because we lack intelligence, but because space-time itself may not allow easy passage across its scale. Interstellar travel is not just an engineering challenge waiting for better technology. It is a confrontation with the deepest structure of reality. Rockets can be improved, materials can be strengthened, energy sources can evolve, but the speed of light does not move. Time dilation does not weaken. The fundamental equations do not negotiate. For centuries, humans believed the oceans were impossible to cross. Then we crossed them. We believed the sky was unreachable. Then we flew. We believed the moon was forever distant. Then we stepped on it. Each time, the barrier was practical. The barrier was technological. This time, the barrier may be woven into the fabric of the cosmos itself. That possibility changes everything. It suggests that civilizations may rise and fall on isolated islands of stars, that the galaxy could be full of life, yet forever separated by distance and time, that intelligence might bloom in countless systems but never truly meet. If the universe is so vast, but built in a way that we can never truly cross it, was it meant to be explored or simply observed? If this video expanded the way you see the cosmos, take a second to support the channel, like this video so more people can discover it. Subscribe for more deep explorations into the physics that shapes our reality. And stay curious, because the universe always has more rules waiting to be uncovered.